Gas laws. These are the mathematical relationships between temperature, pressure, and volume of a gas. So let's quickly review a couple things we know about gases. Number one, they're easy to compress. They're easy to compress because two things. Number one, large spaces between the particles, and also that we can get those particles to move a lot. They also expand rapidly. They move around. They fill their container. That's also important, or also based on the fact that these particles move a lot. They don't necessarily move fast, but they move a lot. And then they occupy much more space because they're moving around so much. Okay, we're going to kind of use some of those things. We're not necessarily going to refer to them all the time, but we're going to kind of work with those. So we start out with Boyle's law. And here's a picture of Robert Boyle. Not that it matters. You don't need to know who he was or when he was, but just so you have an idea of how long ago Boyle's law was discovered. And he discovered, or he studied, the relationship between volume and pressure at constant temperature. And that constant temperature thing is going to be kind of important. And what he ended up finding out was that it was an inverse relationship. And what that means is if you increase the pressure, you're going to decrease the volume, which should make some logical sense. Mathematically, it looks like this. Now, you don't need this part or that part, but this is how we build the mathematical relationship. What you do want is the yellow equation at the bottom. That is what we are going to know Boyle's law to be. Okay, we'll do some examples a little bit later. The next one is Charles' law. Now, Charles is named after a French chemist, Jacques Charles, and I'm a product of the 70s, so I'm the last person that should be talking about anybody else's fashion sense, but Jacques, come on. Qu'est-ce que c'est? Again, you don't need to know about Jacques, when he was, who he was, but you do want to know the relationship between volume and temperature at constant pressure from a logical point of view, which is direct. If I increase the temperature, I will increase the volume. And we kind of know that if you heat things up, they tend to expand, gases particularly. Mathematically, it looks like this. Now, I need you to understand that this is a different kind of relationship than the one we had before. Again, you don't need this part of it or this part. This is how we build the mathematical relationship, and we end up with Charles' law looking like that. This is the one that we need, volume 1 volume over temperature 1. Now, I do want to point out that if it's more convenient, you could flip both. So you have temperature on top, volume on the bottom for both sides. But that's not really important right now. And then Gay-Lussac. Gay-Lussac, and I don't know that we do have a picture. Again, same thing. I don't need to know who he was or when he was, but the temperature and pressure at constant volume is also a direct relationship. And that, from a, let's say, a logical point of view, which I think I've said a couple of times already, is kind of important to know. If I increase one, I will increase the other. Mathematically, kind of like Charles' law, I build it the same way, and similar to the previous two, all I really need is the the final form of the equation. Again, if it's more convenient to have temperature on top, pressure on the bottom, that is completely acceptable. It would still be Gay-Lussac's law. We do come into a problem though with temperature, because if you look at both of those things, picked the wrong one apparently, but if I do look at that, think about what the formula would be if I had a gas at 0 degrees Celsius with that formula as it was. Or what would happen if I was using the Fahrenheit scale, because the patterns should be the same, and not just the patterns, but the numbers, the mathematical formula, I got there eventually, should be the same regardless, but we then have to have a standard. And our standard cannot be Fahrenheit, and our standard cannot be Celsius, because I can also have negative temperatures. And as I said, the Fahrenheit one. So we use the Kelvin scale. Now the Kelvin scale is based on molecular motion, so that at 0 Kelvin, it's the lowest temperature possible. There is no negative temperatures in the Kelvin scale. So it's considered to be the absolute scale, and 0 is absolute 0. Almost more of a theoretical point than an actual one, but that's not really important for us right now. But at that point, all molecular motion stops. So for us, what we need is the Kelvin Celsius conversion, which is Celsius temperature plus 273 is the temperature in Kelvin. And you'll notice on the diagram it's 273.15. We won't worry about that part of it too much. Okay, so For us, I know I didn't say this before, it's just the best place to put it, but we're going to have a standard set of conditions that's called standard ambient temperature and pressure, which is 100 kilopascals of pressure and 25 degrees Celsius, or 298 Kelvin added to 73. The other one is these formulas. So Boyle's law, Charles' law, Gay-Lussac's law. We don't really need to know who said which one, but knowing how pressure and volume, pressure and temperature, volume and temperature, how they're related to each other. And then of course the temperature conversion. Okay, and then we'll try a couple of questions because these are actually pretty simple, straightforward things. The two big things to keep in mind, or the two big places where people go wrong. One is getting three, let's go with three. One, getting the pairings mixed up. So I've got 750 mils at 360 kilopascals. Those two go together. Second thing is, when do I convert the temperature or not? And the short answer is, you're going to convert the temperature. And the third thing is, if you forget the formula, you're going to have this mathematical desire to just go to a standard ratio. Standard ratios will not work with Boyle's law. Promise you that. They will not work with Boyle's law because it's an inverse relationship. But I identify which one is my first, second, and so on. You'll have a question that asks you about volume and temperature. So you're using Charles' law, converting the temperature, and you'll have a question where you're asked to work with pressure and temperature. So obviously, Gay-Lussac's law. Take a minute, pause the video, work those questions out. We'll check our answers in a minute. I'll come back to that in a bit. Actually, if you're pausing it, you can check anytime you want. Hopefully you paused it and you did it and you can check your answers because, again, having answers doesn't help. Getting answers does. Okay, that's it. That's all it is to it. Pretty simple, straightforward. What we are going to do, though, as we move through our gas laws is we're going to add a couple layers. Because right now, for each one of these laws, something stays constant. But that's not realistic all the time. And then what happens if I don't have changing conditions? So those are the two things that we still need to do with our gases. Anyway, talk to you another time.